Okay, it's open. People just start filing in here now. I'll just give another 30 seconds or so here. Okay, we've got quite a few that have joined. We'll let the rest come in as we're getting set up here. Welcome, everybody. This is our last session for today at ThinkTanks 2024. Our speakers are Dave Maurer and Adam Vance of Mesa ETP, presenting on emission control devices for above-ground storage tanks. As a reminder to everyone, please put your questions in the Q&A chat box. Our moderators will view them backstage and bring them for a live Q&A session at the end of the presentation. Thank you both for joining us again here today, and I will hand it over to you now.
Okay, thank you. Again, thank you, and we appreciate the welcome to speak again at ThinkTanks 24. I'm Adam Vance, and Dave Maurer will be joining me today as we talk about emissions control options for above ground storage tanks. So we'll get right into it. So our agenda today, we'll go over several things pertaining to emissions control. And the first thing we'll talk about is what is vapor pressure and what does that have to do with emissions? What impacts those emissions rates will be our next item. Third item is what do emissions control devices actually do? Do we understand how they're actually working and what kind of problems they're actually solving? We'll talk about what happens to those emissions once they exit the tank, and we'll review the current emissions control devices available in the marketplace. And finally, we'll hit on a little bit of future considerations, including K sub C, which is a new proposed standard. So without further ado, we'll hop right into what is vapor pressure, in particular, Reid vapor pressure. So in the above ground storage tank industry, we hear a lot about vapor pressure, but what does that really mean? True vapor pressure and Reid vapor pressure are two values that tend to be closely monitored and discussed. We will focus on Reid vapor pressure, as this has typically a fixed value, whereas true vapor pressure is measured as a function of temperature and will change in different environments depending on the temperature that it's exposed to. So depending on which one you're interested in, each of these vapor pressures will hold a particular value to you in your analysis. So Reid vapor pressure is determined in a controlled environment with testing methods established by ASTM D323. This consists of a sealed pressure vessel of a certain volume that allows a 4-to-1 vapor to liquid ratio. That is 1 part liquid to 4 parts vapor volume. Then a specific temperature of 100 degrees Fahrenheit is applied to that pressure vessel. And in doing so, this method removes variables such as volume and temperature to get a consistent result. So as this liquid is heated to 100 degrees F, the liquid will begin to evaporate, saturate that vapor space. As that vapor space becomes completely saturated, so eventually that vapor will not be able to, or that airspace will not be able to hold on to any more vapor, that vapor starts to condense and go back into the liquid. And so this is the point where we reach equilibrium. This process of evaporation and condensation results in an applied pressure within the sealed pressure vessel. So we monitor and record that pressure in pounds per square inch, PSI, when that equilibrium is reached. And then this equilibrium pressure is the Reid vapor pressure. So when we think of gasoline, we sometimes hear of RVP 7, RVP 10, RVP 13. Those are numbers established in this testing method through this specific ASTM test. The lower the pressure, the less volatile the fluid is, whereas the higher pressure shows higher volatility. So the very purpose of our emissions control devices is to ensure that we limit emissions to the atmosphere. And this information is helpful to know what products might be more prone to emissions and will help in calculating that impact. This is where true vapor pressure comes in, as we know we're not always storing our products in a sealed pressure vessel heated to 100 degrees Fahrenheit. True vapor pressure gives us a vapor pressure at variable temperatures and reflects a more real life vapor pressure. So we talk about vapor pressure, whether it's Reid, whether it's true. We talk about emissions control devices. Does that mean that we are asking our emissions control devices to seal 7 psi or 10 psi or 13 psi? No, the emissions control devices that we use are not designed to seal at temperature. Okay, so now that we have this vapor pressure, what does that mean? What really impacts the emissions rate? How does that play into that? So there's 3 main variables that will impact the emissions rate by impacting the volatility of the fluid stored. The first variable that we look at is temperature. As we discussed with Reid vapor pressure and the true vapor pressure, the vapor pressure or volatility will change with temperature. A warmer fluid with more excited molecules has higher volatility, and that higher volatility promotes additional emissions. This works in the opposite way as well. As we lower pressure, our volatility and emissions rate will decrease. Lower temperature. The next variable is surface area. So emissions only happen at the liquid surface. That is the transition point between the liquid and, in our case, the atmosphere. If we took the same volume of liquid and put that liquid in a tall container with a very small surface area, the area exposed to with a very small surface area exposed to the air, and then put that same amount of fluid, but put it in a very shallow container with a large portion of the fluid exposed to the air, the fluid in the shallow container would evaporate at a much higher rate than the fluid in the taller container. And so surface area is directly impacting how much emissions that we have. And again, this is because emissions happen at that transition point between liquid and gas for the liquid surface. The third variable impacting emissions rate is air movement. If we have wind or airflow, particularly across the liquid surface, we will promote an increased emissions rate. This happens because the airflow lowers the saturation of the air close to the liquid, which in turn promotes a higher evaporation rate. We can think back to the Reid vapor pressure test to conceptualize the attempt of the liquid to emit until it reaches equilibrium. It's trying to release into the air above it. The airflow removes that saturation as it moves across that liquid surface. And so the liquid is continuing to try to reach equilibrium, but because there is such a low saturation at that point now with the air movement, that it offers a higher emissions rate. So we can apply all 3 of these variables to water with evaporation and condensation to help understand and validate this phenomenon. As for temperature, when we think of water, if we increase the temperature or even boil water, we know that the water will evaporate very quickly. As for surface area, water in a glass will not evaporate as quickly as that same water of glass that's spilled on the ground. The spilled water spreads and creates a large surface area for evaporation and hence quickly evaporates. Finally, with air movement, if we have air moving across water, like on a windy day, we can expect the water to evaporate at an increased rate versus a calm day. This is also why we cover our food in the refrigerator so that the airflow doesn't dry out our meal. So now that we've established vapor pressure and the variables that go into promoting or limiting volatility or emissions rates, what are we actually trying to accomplish with our emissions control products for above ground storage tanks? So when we think of the variable of temperature, common emissions control products do not impact the temperature of the stored fluid or the environment around it. We do not try to actively reduce temperature of the stored product, which would reduce the volatility emissions rate. So emissions control is not focused on temperature variables. When we think of surface area, the most common and effective emission control product that we have is the floating roof itself. The floating roof covers a vast majority of the surface area of that volatile product and is responsible for most of the emissions control. Beyond the floating roof, most emissions control products do not impact the exposed surface area of our stored fluids. For example, we are not eliminating the exposed surface of a gauge pull well or a column well. In North America, we typically are not reducing or eliminating the surface area of our rim space or the space between the floating roof and the tank shell. However, there are some products that do indeed reduce or eliminate the exposed surface area, and we'll touch on those a little later in the presentation. But in general, we can say that most common emissions control devices do not address the surface area. So we're left with the final variable of air movement. This is the variable that our emissions control devices are combating. These emissions control devices are limiting the wind and air movement that is trying to reduce the saturation of the air above the liquid surface. In doing so, we limit the emissions release and lower the emissions footprint for the storage tank. The primary method of emissions rate reduction is through blocking or significantly reducing air movement. So we may think that we are keeping emissions in the tank with our emissions control devices, but after understanding the variables that impact volatility, are we really keeping emissions in, or are we just keeping the air out? So now we've talked about volatility, we've talked about emissions and what factors that go into that, and now we're going to talk about the emissions themselves, and they're made up of volatile organic compounds. And in this chart, there's maybe a little bit going on, but we're going to talk about the differences in VOCs, and VOCs are not all equal. As you move to the left in this chart, we have lower boiling point products, higher vapor pressure, so higher volatility products, and we'll offer some kind of examples of what those are. So propane, for example, is a very volatile organic compound. A VOC that falls into the VOC category would be something like benzene. As we get further along into intermediate and semi-volatile organic compounds, they get larger. So this is hexadecane and a larger compound here. So as we increase our size of the molecule, we tend to have a lower volatility. So moving on from vapor pressure and how volatility is established, we can dig a little deeper into what the emissions that are produced in above ground storage tank are. When discussing emissions, and particularly in a permitting discussion, we discuss VOCs or volatile organic compounds. Not all VOCs are equal, and in fact, they span a wide range of molecules and matter states. The very volatile organic compounds have a very low boiling point, and because of this, can be gas form at room temperature. Examples of this being propane, and as you can see in the diagram, it is a very small and more excitable molecule. Volatile organic compounds comprise a mid-range of molecules that are volatile and have a vapor pressure that we see with emissions control requirements in the above ground storage tank industry. So this is primarily where we're dealing with. There are specific molecules that promote the volatility, and an example of that molecule is benzene, as we discussed. A little more complex of a molecule, but a particular focus in emissions is intermediate and semi-volatile organic compounds. And so with VOCs, when we get back to benzene, These are typically vapor pressures. We'll see single digits, double digits, and are again in that range where we're looking at those from an above ground storage tank standpoint to control those emissions points. And so then getting into intermediate and semi-volatile VOCs, these comprise increasingly larger molecules. These molecules can be in a liquid or semi-solid waxy states and generally not considered volatile enough for emissions control in above ground storage tanks. Although there is some research to suggest that these low volatility compounds do impact the environment through aerosol formation. And we'll hit on that for a second. So what happens to these emissions? We have two phases of what these emissions are. As emissions occur, they obviously enter into the atmosphere. The emissions can either be in a vapor state or a gas phase, which is what we tend to think about with emissions control and volatility, or they can be aerosols in which they are not gaseous, but a liquid particle. As aerosols, these liquid particles are able to interact with other compounds in the atmosphere, such as dust or other particulates, and create pollution or smog. Aerosols are classified as primary or secondary depending on their source. So primary organic aerosols typically result from vehicle emissions or burning or some similar activity like that. Secondary organic aerosols are sourced by gas to particle conversions and oxidized hydrocarbons, with some research showing potential sources of those intermediate and semi. The origin of some of these secondary organic aerosols are from intermediate and semi VOCs. So those intermediate and semi VOCs do emit. They are VOCs, but they do this slowly, and that it shows that they are also potential sources of some pollution that we see in the atmosphere. So with that, I'll pass this over to Dave. Dave's going to walk through various emissions control devices that we see in above ground storage tanks currently. This is not an all-encompassing example, but shows some various methods for use in emissions control. So Dave, I hand this over to you and we'll walk through these examples.
Thank you, Adam. As Adam said earlier, the main control device in this picture is going to be the floating roof itself. But where does that leave us? You can't have the floating roof touching the shell. So that is probably the next biggest area of emitting. And again, it's the rim space between the edge of the floating roof and the shell of the tank. And Adam just popped up here. You know, we're also talking on external floating roofs as well as internal floating roofs, but not to the extent. But we get the Coke bottle effect, if you will. It's the wind blowing across of it actually sucks the vapors out and leads to increased emissions. So if we're looking on the far left over here, where Adam just put in the primary shoe seal, you'll see that what we're doing here is covering up the area where the vapors are. So what we've got is a metallic shoe pressed up against the shell of the tank from the floating roof. And then we have a piece of fabric running from the top of the shoe to the rim. And that effectively covers up that area. Additionally, there's a secondary seal on here where it just kind of acts as a secondary containment to that primary shoe seal. Next, we're going to have a ladder cover. You can see that there's a slotted gauge pole in this ladder, and we can put a gauge pole float in there at the time, and seal the inside of that as well if it's necessary. Then we have leg boots. So we've got boots that can cover up the legs, because that's just another 4-inch hole in your tank. And those boots give you a credit as well for dealing with the emissions. We have a gauge pole over here, which we put a cover on. And again, we're reducing the area. There's also a sleeve you can put down in. Does that not come up on the next one, Adam?
It will be in a second.
Okay. And oh, okay, we got some gaskets for this. You got the sleeve that reduces that amount, and you've still got the vapor space area down below it. And then we have a either a liquid filled tube or a foam filled tube seal that sits directly on the product and eliminates the vapor space and eliminates the wind from pulling the vapors out. And then there's the gauge pole floats that can go on the inside of the gauge pole that ride up and down on the product. And they're effectively eliminating the vapor space or vapor areas where the vapors can escape from.
Yeah, thank you, Dave.
You're welcome. Thank you.
So those are just a few examples of, and I'll go back to this last slide, a few examples of some emissions control devices that are available in the market. Again, not all encompassing. When we talk about primary seals, secondary seals around the rim, lots of different options and method of how those primary seals are made or how they operate. Secondary seals can be wiper seals or compression plate secondary seals. The wiper seals are basically a large piece of rubber that will flap up and down as it moves up and down the tank wall, where the secondary seal with a compression plate will have an extrusion on the top of it, and the force of the extrusion touching the tank wall is applied by those stainless steel plates that go around the rim. And again, there's other emissions control devices depending on the application and what's going on with the tank. But generally, these are the options that are available for us when we're looking to reduce our emissions output and to get into compliance with some of the regulations. So I wanted to kind of touch base on what may be changing in the future, and in particular, what's changing with rules regarding emission sources and how we control them. So this particular standard is pertinent to US-based participants, but could have impacts on other markets in the future. The EPA in the US has proposed a new source performance standard called K sub C, where you have been currently following 40 CFR 60 K sub B for several decades, and this is the first updated proposal, update proposed for quite some time. I want to preface this as this is a proposal and has worked through some public comments, but it is not established as a new standard. So this is not a new rule. It is currently being proposed at this point in time. But it's interesting for us to look at and talk about. So what is in this new proposed standard? Many of the old requirements of K sub B remain, including requirements for some emissions control devices and inspection methods. However, there is some language that is more stringent on emissions control, including lower explosion limit monitoring of IFRs and degassing controls. The standard is written to be applied to any new construction, any new tank construction, reconstruction, which would be classified as a certain percentage of the tank is deemed to be repaired, or a modification to the tank. And the language also includes that changing to a higher vapor pressure than what you previously stored. So say you moved from a lower RVP to a higher RVP, that would be considered a modification to the tank and would require case of C to be applied to the tank. So let's get into a little more details and some noteworthy changes that could impact control devices and what those new requirements would be. So first, when we look at IFRs, we see that the requirements in the language in this call for mechanical shoes or liquid mounted primary seals will be required with a rim mounted secondary. So it's a little change. There was some language where you could just have a primary seal in some of these tanks or 2 wedge wipers. It appears that is going more towards mechanical shoe or liquid mounted and rim mounted secondary in this language. And again, a liquid mounted seal would be, as Dave was showing, with the seal directly on the liquid surface, mounted on the liquid surface, where the mechanical shoe is mounted a little bit higher than the liquid surface, creating a vapor space. Additionally, to those new rim seal requirements, there would be annual LEL monitoring and inspection required. If the LEL inspection results in a 25% LEL level or higher from the hatch, this would be considered a failure and would require repair. So not only just visual inspections, this is implementing a monitoring of LEL as well into the seal inspection. For EFRs, external floating roofs, there's some interesting language that creates an either-or type of arrangement centered around the gauge pole and whether the gauge pole is slotted or unslotted. As a background, and we showed this on the diagram as slotted gauge poles, but a slotted gauge pole offers an advantage to the tank owner in that it allows the liquid stored in the tank to have free flow through the gauge pole. This free flow allows the liquid in the gauge pole to be an accurate representation of the liquid stored for sampling, and also allows for a more accurate height measurement of the floating roof, as there's no airlock or potential vacuum. Unslotted gauge poles do not allow liquid flow and can have the tendency to store liquid in the gauge pole that was first introduced on initial fill. That fluid has a hard time getting out of that gauge pole without the slots over time, and so the material and the fluid that you're sampling in that gauge pole may not be a good representative of the fluid that's currently stored in that tank. So the restricted flow also with unslotted gauge poles impacts the height of the fluid. So the height of the fluid in the gauge pole that's unslotted may not be the same height as the actual floating roof, and could lead to incorrect estimations on floating roof location. So the language in case of C offers 2 options around the gauge pole. Rim mounted secondaries remain in effect since these are EFRs for both. So that remains unchanged, but there are primary seal requirement changes. If unslotted, the tank is allowed to use either a mechanical shoe or a liquid mounted primary, as is the current case with case of B. If the slotted gauge pole is used, only a liquid mounted primary seal can be used, and there must be a gasketed sliding cover, pole sleeve, and wiper for your gauge pole. So now the presentation of a liquid mounted primary seal as the only option with a slotted gauge pole may raise some eyebrows. As we discussed, the 3 variables in reducing emissions rates, temperature, surface area, and airflow, the liquid mounted primary seal holds a particular advantage because it is reducing the surface area as well as blocking air movement. So it works against 2 of the variables that impact emissions rate. Because of this, liquid mounted seals have the lowest emissions factor for primary seals, and in some setups can demonstrate a 70% reduction in emissions compared to a mechanical shoe. So why haven't they been used? Traditional liquid mounted seals suffer from poor service life. In the diagram, you can see in the lower right the general construction of these seals. It includes a foam core held in place at the liquid surface. The foam core and support structure are wrapped with a fabric that's suitable for service with the product stored and provides a barrier to the foam and to the atmosphere. These foam seals can put a tremendous amount of pressure on this fabric as they are constantly exerting outward. And over time, this force and friction against the fabric during fill and drain cycles can cause this fabric to fail through wear, rips, or holes. And once the fabric's compromised, the foam can soak up the fluid since it's sitting right on the surface of the fluid, and can cause a seal failure and an environmental headache when being replaced. When you drain and degas this tank, you still have product in that foam, which is problematic. So traditionally, these foam seals have used urethane fabric. And with that, we would expect the life expectancy to be about 3 to 5 years. So while the seal can demonstrate lower emissions for 3 to 5 years, the failure of the seal can create non-routine emissions, such as draining the tank and degassing. That's required to replace this seal. So these non-routine emissions can be much higher emissions than those saved by the seal in those 3 to 5 years. And so for that reason, in North America, mechanical shoe seals are less efficient in emissions reduction, but are used because they are durable and can last those 10 to 15 years or more, while avoiding these non-routine emissions. So the proposal in case of C has some challenges. This traditional method creates a problem for tank owners if case of C is implemented, as reliability is a concern with liquid mounted seals. However, there is new technology coming to the market, specifically a product called FlexCore with armor fabric developed by us here at Mesa ETP and is currently patent pending. This liquid mounted seal addresses durability concerns with some novel technology in fabric that is chemically resistant, but also exponentially more abrasion resistant than urethane. Our analysis and tests showed the longevity of this technology achieves mechanical shoe reliability or even longer. So the regulations around emissions control, as we see them, are likely to become more stringent over the years, and we as an industry need to keep identifying those trends in a search for new technology to support the industry and the environment. So in summary, today we discussed vapor pressure and how it is used to compare volatility between different products. We discussed the 3 variables that impact emissions rates, and those are temperature, surface area, and air movement. Emissions control devices typically focus on air movement reduction, with some designs addressing surface area. Temperature is typically not a focus in emissions control reduction. Emissions results in vapors and aerosols, which both impact the environment in different ways. There are a host of emissions control products and designs in use today, and there looks to be some regulation updates on the horizon, in particular with the proposed case of C that we just discussed. All this to say that there is new technology emerging in emissions control, and that can help combat the challenges now and into the future in regards to regulations and reducing the emissions of these storage tanks. So I want to thank you all for your time today and appreciate the opportunity for me and Dave to present at ThinkTanks 24. Again, this year, it's always an honor to be in front of you all. And so with that, are there any questions we can answer? And I see Alex coming back on to help us out.
Hello, thank you both. Great presentation. Floating roofs are pretty near and dear to my heart. I get on somewhere between 150 and 200 of them every single year. So I'm always pretty excited to see presentations on this kind of stuff. And we have a few more really good ones coming up this week as well. There's a couple of questions here, and we're going to kind of balance a little bit between what we're seeing on the US and on the Canadian side, because the Canadian side has what we call CCME. So it's the Canadian Council for Ministers of the Environment. There was a code put in place back in the 90s that kind of dictated some of this stuff to us, and it really hasn't been altered or touched that much since, with significant updates. We've kind of just let it be and relied on it. In the US, though, in particular, are we seeing significant differences state by state in the air quality measures and what the requirements are, or are we looking kind of at the federal level across the board? There's a minimum requirement, and if there is a more stringent one in a state, I assume that would be what has to be accounted for in that state, right? The more stringent value would be what we're going after.
Right, yeah, that's a very good question. So it's complicated in the US and not complicated at the same time. So you're right in the fact that in different regions of the United States, there are more stringent air quality standards, and that's dictated by the EPA in areas that are considered ozone non-attainment. So ozone levels are at a rate that are not acceptable for the EPA, and we cannot have any more emission sources. So areas include Houston area, Southern California, and parts of Chicago land area. And so those particular regions tend to have their own emissions control or regulatory bodies that are controlling emissions control and have more stringent standards on top of the federal standards. So when we talked about 40 CFR 60K sub B, that is a federal standard. And so that would apply across the entire United States. But in particular, these areas that I discussed have those more stringent requirements and that are not necessarily applied to other portions of the United States. And we're seeing some other areas in states like Maine is adding in new requirements for fence line monitoring of certain facilities. And so there's, in some ways, it's a little bit piecemeal, but this is really kind of the first federal widespread proposed change that we've seen in decades.
Right. Okay. And are those groups working with federal groups as well to develop this, or is it strictly at the level of the state where it's more stringent? If they're developing that on their own based on local or regional climate or environmental conditions, or if you're close to, say, something like a national park that you have more responsibility to protect, is that entirely handled by state, or would they work in conjunction with federal groups as well?
There's a little bit of a conjunction. If you look at some of the state and local area regulations, they really they tie off of the federal requirements and maybe just tighten them up a little bit. And so there's a balance between creating a whole new set of standards that are unique to anywhere else in the country, where you only have so many available products and certain companies that are able to do certain things. And so there's a level on where they can go, but from what types of emissions control products are used, they can really ratchet it up to, say, for example, primary seals and secondary seals on all internal floating roof tanks. That is in place in some areas of the US, where it's now looks like it's starting to be more federal guidelines. And so that's where a lot of the state level and local level is really kind of going for the most effective, lowest emission options, and making that as a requirement for those areas.
Right. Okay. I've got a really good one here on gasoline storage, and this participant is asking here that so gasoline is often stored in fixed roof tanks with no internal floating roofs and only the PV vents to control the emissions. And so the question here is, how effective are PV vents on their own in emissions control?
So the tank needs to breathe, and as from an emissions control standpoint, we don't want to build pressure within a tank at all, and so we're really susceptible to the temperature of that tank at that point. And so as the temperature increases, that has to go somewhere. Now when the temperature decreases, yeah, we'll have to equalize that. But if we're not covering the surface of that floating roof tank, you're really and this could be dependent on how much material is in that tank, the fluid is trying to saturate that airspace above it. And so the more opportunity that we give for that to happen, the higher emissions rate, or that transfer from gas to vapor, or from liquid to vapor, that you're going to see.
And additionally, you'll see changes in product level as the product level is, as the product's pumped into the tank, the vapor's got to go somewhere. And as Adam showed us, it's a saturated vapor. So it's got to go somewhere. It's going out that PV vent.
Right. And we've got a similar thing in our CCME code here, and I've taken a couple of little pieces from it there, but basically for any tanks that are over 9 meters in diameter, which is almost 30 feet for you folks in the US, and if they're storing a VOC with vapor pressure equal to 10 kPa but less than 76, we're supposed to have one of the IFR, the EFR, vapor control systems, and those systems are supposed to be the effectiveness of 95% efficiency by weight. So really, there's not a whole lot of room for error there, right? That's, you know, we're talking about a significant amount of either potentially having to have a vapor control system, a recycle system, recovery, or in some cases, they're even calling for here what we're calling the thermal oxidation, so destroying the vapors outright. So that's kind of just the two different sides to the question about, you know, what are we doing with tanks that have no floating roof? They've got just the PV vents. There's certain other criteria that need to be met. You don't just pop a PV vent on and call it a day and go from there, right? It's got to be able to actually contain within that allotted pressure that's being specified. There's another a couple of questions that are coming up here, and one of them that I'm curious about as well is, so when we look at, you've got a measure in there of 25% is kind of the fail rate on LELs or LFLs for your annual inspections. In our CCME code, it's 20%. Now, the gas testing method that we see in our Canadian code is actually, it pertains more to gasoline tanks. So when you want to explore other chemicals that are being stored, you actually have to do baseline testing for averages over a number of years. So what I'm curious about here is that when we say 25%, are we saying 25% that's across the board? Or are we saying that is specific to the type of product being stored? And do you have a lot more history, or is there a database to pull that information from? So say for gasoline or for an ethanol or some other product, what are the varying limits, or is it just a strict number across the board? Because what we have to do in Canada is we actually have to prove that LEL is not going to exceed an amount above the baseline average.
Yeah, that's a good question, and the standards are not in stone, and so I wouldn't say that I'm an expert on how that's established and what the language is, but from my experience, it would be like you said, on those lower volatility products, establishing a baseline is more sense, but this seems to be targeted more towards high volatility products like your gasolines, and really the way that I was reading it and understanding it to be is it's another way of an indicator that you've got an issue with something, that you're something going on with your emissions control products. So what we're doing with internal floating roofs in particular is really relying on visual inspection, and that's really difficult to do when you're on the top of the tank and you can only see the secondary seal. For example, if you have a primary and secondary seal, you have no idea what that primary seal is doing. And you're trying to see the best you can with a secondary seal, and I'm reading this as just a method to kind of have a backup besides gap measurements and visual inspections to say, is there another thing that we can monitor to see that something's maybe off for us with the emissions control devices we have.
Right. And to that point, of course, the visual inspection is really our first line of defense in terms of determining what's going on. And so we see a variance on a client-to-client basis of them, you know, either allowing people to enter onto a floating roof space, whether external floating roof or internal floating roof, and do the proper visual examinations. But like you said, there are some cases where a tank, you know, can't be locked out for operational requirements. There's, you know, a different level of safety expectation on different facilities or with different products, and that kind of thing. And so what that does is it kind of excludes some of the you know, well, the basic tool that we have in terms of determining what the effectiveness is. So, you know, like you said, we can't even get to the primary seal in a lot of cases to see what's going on. So when we're saying that we have these things installed and they're part of our emissions control, you know, it has to also go along with, are we testing it? Are we making sure that it's adequate just by even looking at it? And we don't always have that. So what kind of things in that case then, what other measures or what other tools can we use to try to rule out issues there that we otherwise can't get at just because of an access issue? Or I've been hearing a little bit of talk about, you know, there's some infrared imaging and things like that, some new sensors and trying to determine release rates and things. Can you speak to any of that?
Yeah, that's a good problem that you've discussed, and I think it's an inherent problem in the industry, and that we've established emissions rates for all these different products, and we base our permitting on what we expect it to be. And then when we bolt it all in the tank, what does that actually mean for the tank? And so when you take a reading, is it good or is it not good? And if you have a limit that's above 25 LELs, okay, well, where is it coming from? And that poses a challenge. And so we've experimented with this a little bit, not so much on tanks in particular, but in some laboratory testing on our end on gas monitors and trying to identify leak points, and those can be effective, but they can also be pretty difficult to use, and they're quite expensive, and depending on how far you are or where you are with potentially airflow and things like that, it may be problematic. And so I think that there's some technology out there, but it still can be particularly difficult, especially with an IFR, if you can't get in there to identify maybe where these issues are coming from, unless it's completely obvious when you open it up and you see a big hole in the side of something. But yeah, there's a challenge with that, and I know that there's some technology out there that, again, we've used, but it has posed a little challenge depending on how close you can get up to the issue and kind of the environment that you're in.
Yeah, and I think along that same line, it's a good point that not only are we trying to determine if a leak of some sort or a release is present, but where it is, and can we target it for more effective repairs, right? In API 653, we've got limits on the amount of seal that can be replaced at any given time with a tank in service. Obviously, out of service, we can do as much as we want. But, you know, we've seen, in our experience, we've seen a lot of different situations where potentially we've got in the vapor space, particularly in the outer pontoon wall face between the two seals, we're seeing that vapor space corrosion, but it's not always uniform, right? So to us, that indicates that there's, a location where there's more release or where the gas is being trapped more than it is in other areas. So, if you're going to set up a monitoring system of some kind like that, it can't be a single source just saying, well, we have a monitor between the two seals because, let's say the tank is 200-foot diameter with a floating roof in it. You might not even have any gas on the other side of between the seals on the other side of the tank if there's little small gaps in the secondary that are releasing elsewhere, but you could have a whole bunch of it accumulating on one side of the tank. So it's a matter of also, having the ability to determine where those leak sources or release sources are. If that's the case, would you give a general kind of rule of thumb for number of sensors or monitors based on tank diameter or something else like that?
That's a really great question. Probably the more the merrier, but a function of the diameter and circumference of the tank. And like you said, the challenge is if you have one, is it really pinpointing that? And when we think about a mechanical shoe seal in the vapor space, it presents underneath the fabric. You actually can get some airflow around that. You can get a current of vapor that's traveling around it, and so potentially only a couple monitors might be able to pick that up because it's going to find that way out. But when you get into one monitor, where is it really telling? You have to be able to triangulate and maybe having definitely at least 4 monitors to monitor where that's coming up. And that's the challenge that I think is presented with us in the industry, is as we continue to develop sensors and monitors and things like that, we can identify that there's a problem, but we haven't quite figured out a great way to pinpoint them quite yet, because we're still using some pretty old technology from the seal designs and some of the other products that aren't necessarily telling us, hey, you've got an issue here, or you've got a hole here, or you've got, and so I think there's potential down the road for that as well, for us to develop a better way to kind of help folks out with this stuff as we develop more and more of these standards that are going to be asking for us to monitor real-time emissions, and that's going to really challenge the industry on figuring out where they're coming from.
Right. And I think there's a lot of value in something like that too, because if you're able to continuously monitor as you fill and empty a tank, you're taking those snapshots of that release or the concentration of release at varying product levels. And I think one of the issues we've seen with just the conventional method of an annual inspection is that we're taking a snapshot really of where the seal is and how things are aligned at a particular product type. But that doesn't mean we have the same gap profile at every single product height in the tank, right? So when we come and see a tank one year, sometimes the seal looks great, and the next year we come back and we've got a whole bunch of gaps in it, and maybe that cumulative gap area actually exceeds the allowable limits. And the question often is, what do we have to do? And really my answer sometimes is maybe just operate the tank at a different height. You might have a flat spot that causes the seal not to fit up properly, and sometimes the answer is simple. It's just don't operate in that range. But if you have these sensors, you're able to monitor in real time, really the hot spots or the areas that you don't want to rest your tank floating roof level at. And I think that being able to account for that at every product height is going to be effective if something like that can be developed and implemented long term. There's a couple questions here about we're getting away from the actual seals themselves, but more over towards the floating roof socks and things like that, and asking about the effectiveness of that. And so, we see a lot of times with like a floating roof leg, there's a sock over it, there's a little clamp. Essentially the idea is that we're able to close that off, but it's not necessarily a fully closed system. So when we have a sock like that on, maybe some of the vapor is captured, but really what's the effectiveness of that? At some point that sock is coming off, it's there's going to be some release. Are we really capturing that much in those? Is it more a method of slowing things down? Is that how we're looking at that?
Well, again, it's a function of trying to keep the wind out of the equation on an external floating roof. I've never seen it, but I believe New Jersey has an edict that if you got a floating roof with a leg in it, it better have a sock on. The socks, I believe that the EPA gives you a credit for having those socks on to the tune of about, I want to say it's like 65%. And I've had an argument with them before about, where's the other 40 coming from? Because, it's perfectly sealed off. I mean, anymore, we have a tape that we send out with each leg boot that goes around the leg for the clamp to really seat in there good. Unless it's torn, or I see them pushed off every once in a while because somebody will use their legs or their leg sleeves as a low leg position. That's why we came up with the stay up leg guard or leg boot. But and there's permeability through the material itself, but it's not that much. And we even proposed to go in and try and do some testing, but they want way too much money to try and do any kind of new testing on it.
Mm-hmm. The sock material specifically for floating roof legs, I'm assuming it's not a one size fits all, the same way with the seals. There's some compatibility issues and things like that. But generally speaking, is there a material that we see used more commonly across the board that kind of can fit a lot of different things, or do we have to get down to this very specific material, permeabilities, all that kind of stuff for every single product that we're storing?
We send out a data sheet, so they're built for your leg. We've got different diameters that we build, and the bulk of them that I see are polyurethane material. Specifically our 6036 material. It's just very rugged, very UV resistant. when you get into some of the other chemicals and things like that, we have another material. It's a 7010 material, which is very chemically resistant.
Awesome. Thank you. There's a good follow-up here about the comments in New Jersey. And actually, this person is confirming here, saying that it's accurate that New Jersey is requiring the SOx on the external floating roofs. So somebody there obviously familiar with what you're referring to and the requirements there. So yeah, for sure. Yeah, I appreciate you chiming in there and giving us an update there. Thank you, Ty. I think that I've got one more follow-up here, and it was actually from the participant asking about the gasoline tanks with PV vents that we discussed kind of at the start of the Q&A session here. They're just a follow-up comment, really just saying that they agree with, you know, essentially what was said here. But part of the problem is trying to convince people, not necessarily in North America, where we know that we have very strict air quality laws, but in other countries. And so what he's saying really is the issue is trying to get people on board with that type of either monitoring or protection of the environment. It doesn't look like every client is actually either aware of it, or there's not that kind of pressure from the government legislation that they are needing to do this. And so just kind of a general comment, I think they're just saying that, you know, this is great that we've got this here where we live, but you know, it should be considered all throughout. If we've got a tank storing gas here in Canada, or if it's in the US, or if it's in the middle of the jungle, you know, a lot of the same rules apply. We're all working together in the same globe to protect the environment. That's essentially what this is at the end of the day with floating roofs. So
I would follow that up with a gasoline tank without a floating roof. There's economic implications for the owner of the gasoline, because there is a lot of gasoline that is being lost to the atmosphere that is not able to be sold. And so with that particular case, it may be a way to demonstrate savings economically. And then the benefits of emissions obviously follow up right behind that.
Right. And I believe we actually have that in our CCME code as well, where it's not just about retaining the VOCs from an environmental perspective, but it is also a product loss consideration for clients too. So it is twofold. And I think maybe the best way to convince people to protect the local environments is to protect their pockets first. So maybe that's the route that we need to take if we want to start you know, really pushing that type of legislation outside of where we already live and have. So
I sat down one time and did some math on leg boots and how quickly they pay for themselves. If just by taking the wind out of the service of an external floating roof tank, they came up with somewhere around 3.5 years they had to survive to pay for themselves. Now in crude oil tanks, it's never going to pay for itself, but there you have an odor issue. So the surrounding environment prefers the leg boots.
Right, and there's going to be pressure from outside sources as well, right? When something smells, that's when we get the heads up that we need to do something. So it's a good comment too. That seems to be like a pretty short amount of time to justify getting the leg boots in place. So, I mean, if we've got a 20-year cycle on tanks, you know, 5 or 6 times paid for themselves, you're set up for life basically on that tank. So that's appreciate the comment. That's great feedback on that too. I think people need to hear some more of the objective numbers like that to do some convincing. So that's important as well. And we are coming up to the last minute here of the hour. So for today, we're going to call it there. I've got no more questions flowing in right now. So just a few people saying thank you very much for the presentation today. Well, thank you both as well for being here again with us this year. We're hoping that you guys are going to join us again next year for ThinkTanks 2025. Always appreciate your time and expertise. And we're looking forward to having everybody back tomorrow morning again for another great lineup of speakers.
Thank you, Alex.
Thank you. Take care.